Hello everyone and welcome to MakeLearn 360. Alright, so in this video I want to teach you deflection of beams and we are going to look at a simply supported beam. Okay, and then a simply supported beam with a point load. Alright, so in other words with a load at the midpoint. Okay, so this is how we are going to do it. Okay, you've been given a beam like this and then you've been asked to find the deflection of the beam. Okay, so the first thing to do is that if you look at the beam carefully, we need to replace these parts with what? A reaction support. All right, so let's say that the reaction at this end, let's call it RA. Okay, RA, and then maybe let's call the reaction at this support RB. Right? Okay, so how can I find these reactions? I'm going to use statics. Okay, so summation of forces. So we are going to assume that the whole of this body is in equilibrium. Summation of forces along the y, every force going up should be positive, will be 0. If we do that, RA, which is going up, minus P, which is coming down, plus RB will be 0. Okay, in other words, we can say that what can we say? We can say that RA plus RB should be equal to P. All right, okay, so let's call this equation 1. Now we can take moment. So let's take moment at one of the ends. Maybe let's take moment about point B here. Okay, let's take moment at point B. If we take moment about point B, then what do we have? So summation of moments about point B clockwise is positive. Okay, then what will happen is that RA, so RA is coming all the way here, so it's going to cause that moment, a moment in this sense, which is what? Clockwise. So clockwise is 0. Okay, summation of moment about B clockwise is 0. Then okay, so RA, what is the moment? The moment arm or the distance is L, that is to say the distance from A to B. Then we are going to take the moment of P, but I see that P is coming down, so it's going to create a moment in this sense, which is what? Anti-clockwise about point B. All right, but then it's going to be okay, so minus, right, P. And what is the moment arm? Because the distance of this from here is actually L over 2 because it's at the center, so it's going to be L over 2. Then should be what? 0. Is that right? Okay, we will not add RB because we are taking moment about B. Okay, so let's solve for RA. Solving for RA will be what? We can say that okay, so let me do it this way. RA will be PL over 2, but L is at both sides, so this L, if I divide through by L, RA will be what? P over 2. That's all. Okay, and then if I want RB will be what? Going back to equation 1, RB will be P minus RA, which is the same as what? P minus P over 2. So it's going to be also P over 2. And this is to tell you that whenever you have a whenever you have a simply supported beam, then the reactions will be halved. In other words, it will take, so if here is P, then here will be P over 2, and then here will also take that reaction P over 2. All right, okay, so it means that the reaction here is P divided by 2, and the support reaction, which is also here, is P divided by 2. All right, okay, so we are done with the reaction side. Let's begin with the deflection itself. All right, let's begin with the deflection itself. So P out of 2, P out of 2. All right, so now that we know the reactions, we can go ahead and then calculate the deflection. Okay, so to begin with, we would first of all take a section. Okay, if you want to do this, you take a section. Let's call this section XX. Okay, now after taking the section, then you try to draw the section. Okay, try to draw the section. So it's going to be like this. Okay, so I have this here. So this is my section, and then there is a reaction here, and that reaction was what? P out of 2. So because I have taken a section, I can call this section, the distance from here, I can call it X. Now let me try and explain something here. This is our simply supported beam. Now, because we have applied a load here, think about the simply supported beam like a ruler. Okay, let's say you have a ruler here. Let's say you have a ruler and you apply a load at the middle. You see that the ruler will try to bend, right? If you have a ruler and you press it inside, it will bend. So we are going to see a deflection which is characterized by something like this. Okay, so we are going to see something like this. So you see that it is going to bend, and that bend is that deflection curve. Okay, you see that it's going to bend inside like that. And then what this means is that all of these are actually deflections. Okay, all of these are deflections. All of these are deflections. But then the maximum deflection that is going to occur will occur exactly at the center. But let's look at something interesting here. You see that at the ends, at X, okay, so we call here at X equals 0, okay, and then we call the end at X equals L. We are starting X equals 0 because we are assuming that this is our starting end and this is our ending. Okay, so that is what the reason why we are taking a section and we are calling that section what? X. So X is varying from 0 to L. That means at any point in time the variable is what? X. All right, so please take notice of this. If I have a simply supported beam, then the deflection at the ends will always be what? 0. Okay. Having known this, let's start with this one. We will talk about the deflection very soon. But before we can continue, this is our section. This is our section XX. But we need to introduce something important here, and that all right, so we are going to introduce this thing here, and then we are going to use it to solve the problem. All right, so you see that we have something like this. There is V which is coming down, and then there is a moment which is going up. Okay, so we are going to use that. So we are going to bring V here, which is the shear force. Then we will bring M here. So M is like the moment due to the cut that we did. Are you okay? All right. So now that we have done this, then let's move forward and then sum forces and moment. By the way, if we are interested in summation of forces, every force going up to be 0 because of equilibrium, then we can say that P over 2 going up minus V should be 0. In other words, P over 2 is equal to V. So this is just telling us that the beam is sort of balanced or in equilibrium. Okay, so we are not interested in this one because we want the deflection. So we are going to sum moments. Let me call it M of X. Summation of moments, positive is clockwise is positive about where we took the session. Okay, we are going to sum moments. All right, but let's look at something here. You see that because of the section that we took, there is already a moment here. So that moment is also going in the anti-clockwise direction. Is that right? So let's call it minus ms. Okay, this moment. And then we have the actual moment from the load, which is what? Coming in the clockwise direction, isn't it? So that moment, because it is coming in that sense, is going to be what? Plus p divided by 2 multiplied by x. Okay, or let me just say x should be 0. Are you okay? So then what is mx? So mx, which is the moment that we are interested in, will be equal to what? Px divided by 2. All right. This is very interesting to know. Once we have the moment, then we can use the deflection equation, which state that ei d squared y divided by dx squared is what? M of x. Okay, and that m of x, or the moment, is what we have gotten. So we are just going to substitute. Okay, we are just going to substitute it, and then so it's going to be ei d squared y dx squared should be what? Px over 2. And then once you're able to do this, then we can actually start with the integration. Please, once you get here, the strength of materials has ended, because don't forget that we are not going to do strength of materials afterwards. Once we get to this point, it is calculus. All right, so we are going to integrate. So let's integrate. If I integrate this ei d squared y dx squared, I'll get dy dx, and then I'll place the constant at one side. Then I'll deal with only the variable. So if you integrate x, you are going to get what? X squared over 2. Are you okay? Plus what? A constant, c1. Always, whenever you do integration, you have to bring a constant, please. Always. All right. Now that you have done this up to this point, this is what you are going to do. So you've been able to come here, but you need to get a relationship between what? C1. You need to actually find C1. So you need to get some relationship occurring here. So please, let's go to the boundary condition. Now, if you go to the boundary condition and you look at it, you see that, so we want to ask ourselves, what is happening to the slope? So you see that at y equals 0 or at x equals 0, the slope is also 0. So let me put it here. So at x equals 0, already we know that the deflection is 0 at the free end. And again, we are saying that at x equals 0, dy dx is 0. All right. Oh, sorry. The slope is 0. Sorry, please. The deflection is 0. Okay. But let's look at the slope. If you come here, in fact, the slope is maximum. The slope is actually maximum at x equals 0. At x equals 0, dy dx is maximum. Why? You remember something that you used to say in calculus, that at the turning point, dy dx is 0. I hope you understand what I'm talking about. Whenever you have a curve and then there is a slope, at the turning point, the slope is 0. Which means that if I take this deflection, the slope here will be 0 exactly at the center. Okay, at the center the slope will be 0, because that is where the turning point is. So I can say that as s equals l over 2, that is the center, dy dx must be what? Must be 0. Okay, all right. So having gotten that, then we can go back into the equation. Then we will say that our boundary condition, so at x equals l over 2, which is the center, our slope is 0. Now, once we know this, then we can substitute that into the equation. We say that ei multiplied by 0, p over, so 2 multiplied by 2 is what? 4. Then x squared, which is l over 2. So please take your time and do it. So l over 2 squared plus c1. Make c1 the subject, then c1 is going to be what? You see, this one is so it's going to be minus p l squared, but you know that 2 multiplied by 2, or 2 squared, is 4, and we are multiply it with the 4 here, so it's going to be what? 4 multiplied by 4. Okay, so basically what I'm trying to say is that it's going to be 4 multiplied by 2 squared, which is 16. Okay, So C1 is minus PL squared over 16. Now, having gotten this, we will go back to the equation and put C1 there into the equation. So let's put C1 to the equation. We will get what? EI dy dx must be what? P over 4 s squared minus PL squared over 16. All right. So please, this is the equation for the slope. So if you have been asked in exams that the slope equation for a simply supported beam, please, this is the slope equation. All right. This is the slope equation that they want. Now, if you if you want the deflection equation, then it means you have to integrate. But before we get the deflection equation, let's find the maximum slope. In fact, the maximum slope occurs at x equals 0. Okay, so the ds will be maximum at x equals 0. I've already showed you that. So then it means that dy dx maximum is given by, if you put x equals 0 here, you see that you'll be left with only, so minus PL squared over 16 EI, because the x squared part will go to 0. And please, this is the formula for calculating the maximum slope of a simply supported beam with a load at the midpoint. Okay. All right. So okay, so that is it for this one. Okay. Now let's try and get the deflection. So if I want to get the deflection, I will take the slope equation and I will integrate. So if I integrate this slope equation, I'm going to get deflection. So let's do that. So EIY, which is deflection, will be P over 4. Okay. Then I integrate x squared. I'm going to get what? X cubed over 3. Is that right? If you integrate x squared minus PL squared over 16, then you bring the x here plus C2. Don't forget that whenever you integrate, you have to bring a constant. Are you okay? All right. Now at this juncture, once you have this, all what you are going to do is that you are going to again look at the boundary condition. So boundary condition. So what is happening? Look at it carefully. If you look at it carefully, okay, so what is happening between x and y? That's what we are interested in. Like I said already, at x equals 0, y is 0. Once you know this, you can go back into the equation and solve it. So we are going to put x equals 0, y equals 0. So our boundary condition is that at where x is 0, the deflection y is 0. So we have 0 equals P over 4. Okay, P over 12 multiplied by 0 minus P L square over 16 multiplied by 0 plus C2. So what does this mean? It means that C2 that we want is 0. Are we happy with that? Okay. So now C2 is 0. That's all. So we will go here. We'll go forward and say that EI y. So P over 12, which is 4 multiplied by 3, x cubed. So P over 12 x cubed minus PL squared 16x, and then plus C2, but the C2 we said is 0. So in fact, we are done. This is the deflection equation. So we call this the deflection equation. Deflection equation. Now once we are done with the deflection equation, then we can go ahead and find the maximum deflection. Why are we interested in the maximum deflection? Because whenever we are designing beams, we want to know exactly the maximum deflection, so that when we are designing, we will know the load that we put on it, so that we don't exceed the maximum deflection. Okay, so for the maximum deflection, let's go back to the diagram and look at it. So you have a curve like this. Where do you think the deflection will be maximum? Technically speaking, you can see that the deflection is going to be maximum exactly at where the turning point is, right? So for a simply supported beam with a load at the center, always you will see that always this side will be the deflection will be 0. The this is what I'm trying to say. At x equals L over 2, which is the center, the slope will be 0. But that is where the maximum deflection will occur. Please take notice of this. For a simply supported beam with a load at the center, the deflection is maximum there. However, the slope is 0 over there. Okay. So we will come here, and then if we are interested in the maximum deflection, we can say that at S equals L over 2, Y is equal to what? Y max. So let's put it inside and do it. So it's going to be what? EI Y max P divided by 12 L over 2 cubed minus P L squared over 16. Then we multiply it by L over 2. Okay. From here, then we can say that EI Y max is what? That is, so P L cube, right? So we've got 12 multiplied by 2 cube, isn't it? And that is 96 minus PL cube. 16 multiplied by 2 is 32. Is that not it? All right. So, okay, let me do it so that some people will be happy. 16 multiplied by 2, 32. Okay, I think now you are okay. So, so that is it for you. At this point, okay, so at this point, let's do something here. Because we have PL cube in common, we are going to factorize out PL cube out. Okay, let me bring it here. So let's factorize out PL cube. Then let's do 196 minus 132. So minus 1 over 96. So this is what I'm saying. 1 divided by 96 minus 1 divided by 32. Now what is it? So minus 1 over 48. So it means that you are going to get the final answer as Y max is what? Minus PL cube over what? 48. And then making Y max the subject, then we can get Y max to be what? Minus PL cube divided by 48 EI. And this expression that we have gotten here is very, very, very important. It means that whenever I have a simply supported beam with a load at the center, then the deflection is given by minus PL cube over 48 EI, the maximum deflection. Okay, so that is the end of the video. Thank you very much for watching.